Sorry? This one cannot. No, I think this is spoil. I don't think it's spoil. I think it's no battery. Is there a battery here? Oh, I see. I'm so sorry. So sorry. Thank you very much. Alright, very good morning. Okay, so first things first, I'd like to remind you to basically post a reflection in IBLE. Okay, it is true that you get experience points. Those of you who haven't been getting any, it's probably because you haven't been doing any. And then you'll be given, even if you put something really inane, you probably get some small amount of points. Okay, but typically, you write something a little more sensible, you get more points. And every week, the tutors will be reporting to me, and then they will kind of compute and see how much you have written, and then they give some points. Okay, I think today's last week. So typically, they give out the experience points on Wednesday. 1, 2. Thank you very much. Okay, thanks. Thank you. All right. Okay. The bad business. Right. So I'll encourage you to basically do some reflections, and even if you don't want to write anything, I'll encourage you to read the what's being posted. Okay. So just a quick reminder. Okay. Next, today I want to announce the results for the 2D and 3D contest. Okay. So before we tell you who wins, let me just tell you who are the finalists. Okay. And it turns out, okay. Obviously, all those people who submitted entries have gotten some experience points, right? And what's going to happen is, once the results are announced today, you will have more. Those of you who are finalists and those of you who win obviously get more experience points. Okay, so let me just quickly go through the list. Okay, so we'll start off with the finalists. Okay, for the 2D. Yang Mansen. Where are you? There, okay. Okay, then we have Shenzi and Eldrick. Hey, what is that? The top thing? What is that? I'm not sure. Burning ship fractal. Okay, I couldn't figure out what it was. Okay, then Chan Jianlin. Let's see. Oh, okay. Yang Zixing. Okay. Eugene Cheong. Not here today, right? There, okay. Very good. Yi Chen is here also. Finally back from Cambodia, right? Yeah, okay, good. Big Jun, where are you? There, okay. What is this, guys? It's ugly, you know. I don't know what it is, but okay. So 3D, for 3D, these are nominees in here. So like the Miss Universe, like the parading now, haven't win yet. Okay. Then nominees for the 3D rules are the following. This one is the Duff. Hey, typo, sorry here. Liu, okay. What is everything? He's having a good time. Okay. Then there is this one also. Liu Haoran and Yang Zixing. Okay. Then we have the Snowflake, Yang Mansen. Snowflake. Han Lin has this hard thing. Okay. Mansen again. I don't know what this is, some kind of ball stuff. Eugene. Okay. So that ends the parade. So sadly, there are no, the auto stereogram a bit jalat, okay? Because first of all, apparently, I think the average word count for the stereogram is 2 or something. So I think apparently a lot of people cannot see. I looked at them, I also wasn't that completely impressed. So this year there will be no, sadly, so thanks to those of you who have submitted the stereogram entries, sadly there are no sort of finalists, okay, for the stereogram. Okay. So now we will announce the results of the competition, of the contest, and you get, those winners get this little green badges. Right. Okay. So they come, these badges come in a variety of colors. Today's what color is this? Green, no, it's not white, it's green, I think. Okay, anyway, there are like a few colors. There's blue, green, red, and black. Okay. And there'll be other contests along the way. So one of the things some people try to do is collect the whole set. A bit like Hello Kitty. Okay. Okay, so first of all, 2D contest. The winners are drum roll. Okay, very good. Tan Jianlin, was this? Okay. There you go.
I like to say I made this out of squares only.
Apparently, it's good. Actually, it looks better. Here it looks kind of weird, but I look a little bit better on the screen. Next. And the second one, I have no idea what this is. It's not around. Okay, come, what do you come? Let me come. Collect for him. I have no idea what this is. But okay, thank you. You can send it. Okay, so these are 2 winners. They have the most number of votes. They have almost, I think, almost 30 votes. Okay, 30 something, high 30 something. Okay, then Holution goes to Darth Vader. How run? So this one, so you don't have to use a shader to win. Apparently people like this also. Okay, congratulations, well done. There you go. Okay, and the last one will be the anaglyph winner, which is the 3D glasses thing. It goes to Snowflake. Okay, so this ends the first contest. There are more contests right now. I think it's ongoing one whereby you're doing the pancake flipping, right? Okay, so there are more badges we won, different colors. Okay, all those of you who participated, okay, good job anyway. Those who won, good for you. But this is kind of fun, right? So hopefully you continue to do more of this stuff. Okay. All right. So today we will continue to do 2 things. First of all, we will talk a bit more about data abstraction, how to implement data structures. Okay. Okay. So let me just quickly highlight this. Although your midterm will cover everything until last week, right? It turns out that at this point in time, we are going to be covering a lot of ground. Okay, the strange thing is this, I mean, there are not that many new concepts to teach every week. So you will be seeing a lot of application of old stuff. Okay. So I would not recommend people, just starting this classes and then not worry about what I teach you. In any case, this stuff will be covered in final exam, so kind of escape, right? So I would pretty much encourage you to continue to focus on what I have to teach. Okay. So today, just going to do more stuff for data abstraction. First one, we'll cover some implementation of data structures. Okay. Secondly, after that, we'll talk about this, how do you manage multiple representations of data. Okay, so let's do some recap. So this is a basic example, a very simple example of data structures. Right? We use this for the name game. Okay. The 2 key ideas here. First is that there is this idea of a specification. okay, which is a contract, right? It tells people what the data structure does, but it doesn't tell people how it's implemented. Implementation is what you do inside, okay? And you do have users of the data structure to know, and you have choice as to how to do it, okay? Alright, so specification again is the overall conceptual design, right? You must, well, typically you will list out the assumptions, what it does, what it doesn't do, okay? And then you have examples, okay? This one you will probably see something like this for the exam, okay? Because you'll some examples. Okay, and these are types of operations. So two things I have. Okay, the data structure itself is useless, right? Because data structure itself pretty much just stores the data, right? You obviously want to operate and do some stuff. Okay, these are the basic kinds of operations. First thing you do, you can construct it. You can create a new instance of the data structure. You can also, typically data structures are complicated objects, right? They basically have parts inside. You have selectors whereby you can actually take out parts of the inside. Okay, predicates are testing kind of functions. You basically check whether condition holds, right? And printers display the data. Okay, so quick example. So we'll do a few examples today. First one is pair. Okay, a pair is really a const block, right? Okay, and a pair is called an ordered collection of two objects. Okay, so order is important because the point is that 3, 4 and 4, 3 are not the same object. They're not equivalent. Okay, so the spec needs to very clearly specify this kind of conditions. So if you say that a pair of two objects is not quite good enough, right? It's not specific enough because you have to be very clear, because otherwise people use it wrongly and bad things happen. Okay, so specs, what else? Okay, constructor. Typically you will have the constructors. So the const box is created using a const, obviously. Okay, your selectors, what are they? The car included. Predicate. Not pair, but pair. Okay, the last one. Okay, display it. Okay, what's the contract? Contract is very simple, right? Contract is the following, right? Basically, if you car the const of xy, you get back your x. You CUDA the const xy, you get back your y. This is exactly what we said last time. Okay, it's a very basic sort of definition, and any definition that satisfies, any implementation that satisfies this definition is actually satisfied sign the contract. Okay, so it's fine. Okay, list. So a list is either an empty, okay, or is a pair whose CUDA is also a list. Okay, so the definition of pair was given in the earlier slides, right? So a pair is an ordered pair of two objects. A list is either empty or is a pair whose CUDA is also a list. Okay, so this is actually a recursive definition, right? Okay, and constructors will be what? This and const. Okay, and then selectors, the car CUDA again. Predicate. Actually, there's also a list and there's a pair and a noun. Printer, just display. Okay, so the next thing, the last thing. Okay, so those two are very simple examples. Okay, today now I will talk a bit about this slightly more complicated example. Actually, I asked them to do this right for homework. Okay, so I think Nanya did this right. Okay, so I haven't had time to look through your homework, but yeah, but this is how we can look at it again and see. Okay, so a set, okay, in contrast to a pair or a list, is actually an unordered collection, which means that order doesn't matter, okay, and also it doesn't have duplicates, so it doesn't contain the same object type. Okay, so the question is, how would you implement something like this? So the idea here is 1, 2, 3 and 3, 2, 1, 3, 1, 2, they're all the same thing, okay, because they contain the same object. Okay, and this is empty set. Okay, this is not a valid set. Okay, 3, 3, 1, 2 because you have a repetition of 3. Okay, not valid. Okay, so what we do is the following. We obviously define the specs. Okay, and in this instance, we say that there are 3 constructors. There's big set, which obviously creates the empty set. Right. Adjoint set does what? Adds an element to the set. Right. Union and intersection does the obvious thing. It creates the set which is union, or the set which is intersection of 2 sets. Okay, we have two predicates here, okay, which is that element of set. You check whether an element is the element of a set, okay, and whether set is empty. Okay, so the first thing to do is obviously that's why it's contract. So there are a few examples. First of all, if you adjoin an element x to S, then obviously x becomes an element of that set. Okay, which means that if you add x to S, obviously x will be a member of that set, because it's inside the set. No, but if you duplicate it, you will still have the set inside. I mean, the fact is duplicate means the guy is inside already, so obviously this is true, right? It has to be true. Okay. Now, if your x is an element of the union of S and T, then obviously either x is in S or x is in T or x is in both. Right? Okay. So these are the two kinds of contracts that need to be satisfied. Alright, so the thing of implementation is the following. In general, okay, how many ways are there of doing this? Huh? How many? That's the right answer. Infinitely many, Okay, it's just that some ways have smarter others, right? So there are technically infinitely many ways of doing this. Okay? And the question now is how you do this. So the first thing you do is to figure out a representation, basically internal representation on how you want to represent the set. I think this afternoon we are doing this also. Okay, I think we're doing something similar. This is a representation. Okay, so the thing to understand is that the choice of the representation will affect essentially the time and space complexities of the operations. Okay, and if there are certain constraints on representation, you should also specify. Okay, for example, in the rational, okay, last time we talked about rational numbers, right? You're not supposed to have denominator equal to 0. So this is something that you need to specify. Okay, basically, if you have representation and the denominator is 0, then it's not a valid object. Okay. Okay, then after that, obviously, once you figure out how to represent the object, your job will then be to implement all the operations. Okay, that's all. It's quite simple. And the last thing to do is make sure that after you implement the operations, right, your stuff will satisfy the contract. If that happens, then you're done. Okay, so let's take a look. So the first thing you can do, the obvious thing you can do, is to do what? You just use the list to represent the set, right? So you don't care. Okay, empty set represented by empty list, right? And then the set is represented by a list of the objects. Okay. The only thing you need to make sure is that you must try to make sure that you avoid duplicates. Because that's the whole definition, right? You can't have duplicate objects. Okay, so the following. Constructor, how do you construct a set? Make set what? Now, right? Okay, because you make set is an empty set, that's fine. Okay, and the way you construct bigger sets is that you adjoin stuff to the empty set. Okay, predicate. Now lah. Okay, there's no if. Why? You can go if now, true, false, right? But then it's the same thing. Okay, so you can just do now. Okay, element of set, how do you do this? So the question now is that you want to test whether X is a member of the set. So how do you do this? By what? Recursion, right? You can do member lah. Okay. So the thing is that basically the simple thing is recursion, right? If it's now, there obviously false one inside, right? Otherwise what? You check what? The car, right? Okay. Otherwise, and that you do what? You do recurse down put it down the list, right? Okay, so this is a very simple, okay. By now, this one is, okay, all you should do is to see this and do this in your sleep, right? Correct? If not, you better make sure that by next week, end of next week, you can do this in your sleep, because confirm the final exam, that's not final. Midterm exam, you have stuff that's obviously more complicated than this. Okay, so this is a very basic thing that you must be able to just cop out. Okay. Alright. Next. Time complexity. Again, almost certainly your question in the exam asks you, this thing you write something. What is the time and the space? Okay. Time. Okay, first, before you go time and space, you first thing the question is what? What is this, right? Iterative or recursive? Hey, iterative. Recursive. Recursive, iterative, okay, okay, this is a hand game, this is a Kichu game, yes, Kichu. Okay, those who think is recursive, Kichu. Anybody? Kichu is raise hand, right? I learned from lesson, man. Okay, so who thinks iterative? All iterative. I thought you're supposed to be recursive, man. How do you? Okay, how come you all say it's iterative, Because cannot find its operation, right? Now, every single thing is like this, right? I mean, remember, every proceed, right? Obviously, is this thing, you have a base case, and you have recursive like, right? So the only difference between recursive and iterative is has to do with the base case, right? Not base case, right? Default operation. You can't find it here, so this thing is iterative, right? Iterative means that the space is what? Typically, unless it's called some weird thing that has a bigger space, right? Okay? And what's the time here? N. Okay, so again, how do you, again, to think about time, how do you think about time? So the first thing to realize is this, you start with n, right? You end when? You end when the set is empty, right? So essentially n goes to 0, correct? Now, then the next thing is you ask yourself, what happens in each step? In each step, n reduces by 1. So obviously, you think about it, you realize that you kind of goes down from n to 0 in about n steps, which makes it linear. Now, in all the log things, basically what happens? The n will half, right? Okay? So this is a simple idea. So basically the idea is that the time complexity depends on how fast your recursion index goes to the base case. The base case doesn't always have to be 1 or 0. It can be anything I feel like it. It can be evil, but the whole point, remember, you're going from some index value n to some base case. 1 and 0 are common, but may not be. Right, so the whole point here is to understand how fast they move to the base case. So time is order and right, size of set. Space will be linear because of the constant space. Okay. So let's look at the next set in the constructor. Okay. So you want to add a non-element to the set. How do you do this? If X is inside a set, then what you do? Do nothing, right? Inside what? Okay, if it's not there, no need to pen cons. Okay, another thing is this, you better go and get your mind, wrap your head wrapped around these three things, right? The cons, the pen, and the list. Okay, confirm will come bite you in 2 weeks if you don't know this thing. I say again, your head be very clear. Okay, so one temptation is this, when you're writing code in Dr. Racket, you don't care, whack one, cons fail, never mind, try a pen. A pen fails, now I try list, right, correct, Okay, very good, if you try this in Dr. Scheme, it works good for you. Guarantee you, midterm exam, you don't have a chance to do Dr. Scheme. So if you do this by anyhow whacking, good luck to you. Alright, it's not that hard, it's not that hard, okay, you don't need to memorize anything, you need to know, understand what these things do. Okay? So make sure you understand the difference between a pen, cons, and list. Again, this thing, what is this? Time complexity. Constant, right? One set need count him, correct? Huh? Order n. Why? But then very simple, what? One set only, you check whether it's true, not true, you do something. Because why? Because you have this thing dominating the time, right? How long is this thing? N. So this guy will not be less than n, right? So either answer is n. Okay, space. I don't know if I forgot space. Space will be 1, right? Because why? This guy is only 1. This guy is also 1. So altogether is 1, right? Okay. Then intersection. How do you do this? You take 2 sets. Intersection of 2 sets. Anybody? Yeah, you can do this many ways, right? So the obvious thing is that you take one set, right? You cool down the set, and then you do what? You test whether or not this guy is inside the other set, right? Okay, and I leave it for you to do for fun, okay? So the other idea is, okay, so first of all, you at this point, the first thing you have to do is learn how to go and write these things and solve these things correctly first. Okay, efficiency is not entirely important, but you should be doing completely bad things. This one, a simple example would be, you take one set, I say again, you go what? You cool it down the set, and then take the car, each car, you do what? You test whether it's a member of the other set. If it's a member of the other set, you do what? You consider back, right? If not, you ignore it. Okay? So anyway, do this exercise. This is a rather simple exercise. Okay? How fast is this? Why? Okay lah. Okay. If you use M and N to specify the two set size, it's something like a product of two sizes of sets, right? Because as Jen says, you need to take each of elements in one set, compare it with every element of the other set. Okay, so this is how it goes. Okay, so what you've seen here is a very obvious way of doing this, right? It's a very straightforward way of representing a set. Okay, now let's look at a slightly different way of doing it. Okay, now what we do is we're going to represent the set as an ordered list. That means now the objects are not just put in randomly, they are actually sorted. Okay, and obviously same thing, make sure you no duplicate. Okay, the question is why in the world would you want to do this? Say again? Scheme is pretty useless. Yeah, so the point is that, okay, technically, okay, we will see very soon what we do, but then the point here is that obviously just make it faster. Okay, so the moral story is this, in life, typically everything is trade-off. Okay, so what we're doing here, okay, remember last time, anything interesting? Okay. Okay. So the point now is that you can't manually search, which we will learn later. But then the point here is that, okay, remember last time the rational number thing, right? Not rational number, the rational number thing. So the point here is that you can either convert the lowest terms at the beginning, or you can convert the lowest terms at the display. So the point now is that you can actually choose to pay now or pay later. So here what we're doing here is that we're going to pay early. We're going to basically build a list that's ordered. Okay, why? Let's take a look. So the specs do not require this. Okay, the specs don't say anything about the specs do not at any time basically specify how the representation must be done. Okay, but we have basically imposed special constraints. Okay, now this particular order constraint is only possible, right, if you have some kind of natural cardinality in the object. Basically, it's sorted. Okay, so for example, let's say, I don't know, think of something that can be sorted. What? People. But it can be sorted by height, right? Yeah. So, but there are objects that are not quite comparable. Okay. So colors, yeah. Okay. So colors you can't really sort. Okay. Sort by what? Hex value. Okay. So think harder. Okay. But anyway, numbers can be sorted. Okay. So strings can be sorted, right? Because there's a lexicographical order. Colors, okay. So we were going to say it's not sortable. But then obviously you have to write maybe by the hex value you can. Okay. So anyway, the constructor same thing as before. Okay. Now the next thing, element. So how would you test the element now? Same thing as before, right? If it's empty, it's not there. But then otherwise what? Basically you check that if it's equivalent, it's okay. However, the moment you are bigger than the tested element, right? You will stop. Why? Because it's sorted. Okay, so you know that you will never have bigger something that's equal after that. Complexity of this thing. So it's still order n, right? Okay, but it's on average faster by half, right? Correct, because the point is likely to be faster by half, okay? No. When I ask you for order of growth, you tell me order n. But I'm just saying that, you know, you think about this problem, it's quite clear that it's not the same, right? It's actually faster than another case. Okay, let's take a look at how it works. Okay, so if you look at how this works is the following. Okay, sorry, this is intersection. So intersection, how would you do this? You would do the following, right? You would actually, okay, you would have two sets now, and you know that the two sets are now sorted. Okay, so what you do, intersection, you do what? You will do the following, you take two sets. If they're both equal, take it out and put it in the intersection, right? If not, what you do? Yeah, you essentially advance the two sets, right? Okay, and essentially, if the first one is equal, take out 1. After it's 3, 4, what you do, you advance the smaller set, right? Okay, and then after that they are the same, you take out, and then you keep doing this until they meet again. You take out, and then when now happens, what do you do? You're done, right? Because you know one set is now, the other one is something, then obviously the section will be now. Okay? So this is all the stuff you took out to compare, right? I mean the ones that are the same, you took out and you keep them together. Alright, so intersection, how would you actually implement this? First thing is base case, right? Which will be now. Okay? So if either set is now, you return what? Now. Otherwise, okay, so this is where, again, okay, example here is the use of let. Because now you have these two elements which are the first elements of the two sets, the cars, right? Okay? So for convenience, what we do is that we take them out and call them something, okay? You call them x1, x2, right? Because otherwise, okay, the next few sections is a lot of comparison things, right? So the whole point is that if you call them by car, it's possible, but it's kind of nasty. Okay? So, right. So the thing is this, so the first of all, the two are same, what do you do? You const the guy, and then you call, so you const the guy out, okay? x1, x2, doesn't matter, right? That's the thing, right? So you const out this guy, and then you call intersection on what? CUDA of both sets, right? Okay. Okay, this actually is just implementing what we described just now. Okay, so the two Pauline and Paulina, they are very excited about this, right? What's going on? Huh? And you're not very good friends, right? Because your name is first by just a vowel. So how? Questions? Okay, alright, so after that, what happens is, after that, you do what? You test for which is greater, which is less, right? And then do what? Suppose your x1 is less than x2. Okay, it essentially means that the two elements in front, they are different, right? So you throw one away. You throw the smaller one away, right? So you don't const what? You cannot const, okay? Basically, you throwing the thing away, and then you are putting down the first set. Okay? Leaving the second set untouched, putting down the first set. Now, if on the other hand, okay, basically the three cases, right? x1 either equal x2, x1 less than x2, or x1 greater than x2, right? So, basically, you do the converse. What's the time capacity of this thing? Okay, the worst case will be what? The worst case will you have to traverse both lists until you leave only one element somewhere, right? Because you're going down, then along the way, one guy empty, the other one empty or not? Not empty, right? Because no way those guys are empty at the same time, right? Well, except unless you take away the last element, okay? But typically, the point is that you go to empty, and the worst case will be n plus n, right? So this will be linear, right? Pretty much. Okay, next. Okay, so this tells you, okay, obviously you can do intersection, right? Oh, sorry, union. Okay, so how do you do union? Okay, anyway, at least you think about that, okay? Union. Okay, now the last thing is this. You can, somebody said, right, cannot do binary sort, right? Okay, so the last thing we're going to do is this. We can actually represent the whole set using what's called a binary tree. Okay, so the empty set is represented by the empty tree. Okay, and essentially we must take care to avoid duplicates. And then last thing is that we want to make sure the objects are sorted. So how does it work? Okay, so a tree essentially is of the following shape. Okay, first of all, a tree consists of nodes. Okay, each node contains one object. Okay, the left tree is smaller than it. The right subtree contains objects that are larger than it. Okay, Harlin, wake up. Okay, so this is the example of a tree, right? So 7 is the object at the top of the root. Okay, everything on the left subtree, they are smaller. Everything on the right subtree, they are all bigger. Simple. It turns out this is also a valid tree. Okay? So it means the root can be 3, and then everything on the left is smaller, right is bigger. Okay, question. How many trees are there possible for a set of size n? Okay, this one is not infinitely many, there's only a finite number, okay? So for kicks, you go figure out, given a set of n objects, they are all distinct, how many possible trees are there? Okay, and this is another possible shape. Okay, so all these three different examples, they are actually valid binary trees. Okay, they satisfy the property I just said. Okay, so these three trees represent the set 1, 3, 5, 7, 9, 11. All the odd numbers up to 11. Okay, so these are 3 examples. Okay, so how do we do this? Okay, first of all, we need a way of creating these kinds of trees, right? So the first thing is that the big tree where it has 3 things. There's an entry, there's left subtree, right subtree. Okay, and what we do is we use the list. Okay, and then the tree. Okay, so this first big tree is a constructor for the tree. Okay, these 3 fellas, entry, tree, left, right tree. These are the what? Selectors. Right, so I'm creating here a very simple data structure, which is a node of a tree. Okay, and then after I have these selectors to help you access different parts. So it's a very simple idea. So, okay, if you think about this, this is equivalent to what? It's equivalent to a 3-box cons, right? Okay, a cons box has how many pointers? 2, right? Okay, but here what I'm doing now is that I am artificially creating a third box, right? Because now you think about it, each node is like a kind of a 3 boxes, right? One box points to a left tree, one box points to the right tree, and one box gives you the number, right? Okay, very simple. All right. Now, first of all, how would you test whether an element is an element of this set? What do you do? Base case is what? Okay, base case is very good. Our base case now is false, obviously, and if it's empty, obviously cannot contain it. Then, if not, how? You check whether the element at the current node is equal to, right? If equal to, then you are done, right? If it's not, that means what? It's either smaller or it's bigger. Then you either go left or right, and then you basically do what? You call for a recursion, right? Okay. So very simple idea. If it's equal, you're done. Okay, you look at the current set is a node in the tree. If the current entry of the set is true, it's equal, then it's true. If it's not, okay, if it's less than, then you go down there. You do what? You will recurse down the left subtree. Okay? If it's not true, then you will recurse down the right subtree. Eugene, how? What are you pointing? Huh? Ken? Simple, right? This is okay. These are, like I said, okay. It turns out that after last lecture, most of the things that you will see moving forward are kind of the same old thing. It's the same things that we talked about in class, applied to different scenarios. Okay. So this is not new. How fast is this? Correct. That was 3. So the first thing you look at this is obviously this thing. Worst case is the step on 3, and del 3 is worst case is n. So how? But on average, you expect this to be a normal tree, balanced tree, so you'll be log n. Okay. So adjoin. Yes. No, log n is not worst case. Log is not worst case. Yeah, okay. Good point. We will cover it later. Okay. So but on average, okay. So you're actually preempting me. Okay. All right. Before that, let's talk about this adjoin. Adjoin one means like you want to add a new element, right? How do you do this? You want to see whether basically if it's empty set, you add a new element, right? If not, what you do, you check the current element. Is bigger, equal, or what, right? Can be equal or not? Then how? Then don't do anything, okay? If it's equal, do nothing, right? Simple, If it's not equal, then it's either bigger or smaller. You will go down the left side or right side, okay? And then that's all, basically done. Okay? If it's x is less than the current one, that means it's a which tree? Means the number there is less. Okay, take a number. This guy is less, so you must go down. You must add it to the left tree. Okay, so you make a tree, and you make the entry. Okay, for the set. This is the left tree, and then you join the set to left side, to left side. Make sense, huh? Okay, I say again, you look at this tree, right? Okay, and now you take the first element is actually the entry of the set. Okay, now at this point, you're not doing any mutation, right? It means the trees don't change, right? So you need to create a new tree. So what you do is that you create a new node with the current node as the entry node, right? And then the right side remains the same, right? It's the right branch of the tree. The left branch, what happens? The left branch will be the original left branch with the current new object adjoined to it. Okay? Are we clear? Okay, so you need look at this more carefully and make sure that you understand the logic. Okay, similarly, if it's the other side, you do what? You do the same thing except now it's on the right branch. Okay, now the thing I want to highlight is this. Okay, if you haven't figured out by now, sitting in lecture and listening to me and ensuring that I make sense is actually easy part. Okay, you all realize that. Okay, the thing is this. So I said this very carefully. I said before that if you come to lectures and you understand everything, it's good enough, right? No read textbook, correct? That's what I said. Now the funny thing is that to make sure you understand what I'm saying, it's not good enough if you just come here, listen to me, I make sense. Okay, the gold standard is that you must be able to go home, forget everything I said, and reproduce everything I do in lecture. Then it makes sense. Okay, so this is the gold standard. I say again. So just sitting through this thing, having me explain to you, it all makes sense. Is not good enough. Okay, you have to really. Okay, the gold standard here is this: if you are able to basically go home, forget everything I said, and from first principles re-implement and reconstruct everything I said, then you are all set. Okay. So to make sure that you all understand me clearly. It's not just about here, I tell you this thing, you look at it, and then I explain to you, a bit blur, I explain to you, it's not clear, not good enough. Alright. So, okay, so this is exactly the problem that we just mentioned. So Jen said this, why is the order n, order log n? Because it could be that this is dumb tree which is all one-sided, right? So, for example like this, so this is a right tree, is this a valid tree? This is a perfectly valid tree, okay? And if you look at the adjoint set, depending on the order in which I put in the elements, right? If I put the elements in, okay, in fact, the sad thing is this. If I put the elements in sorted order, life is all screwed up, right? Okay, so in order for me to have a nice tree, in fact, I need to put elements in some smart way, right? Random is not good enough, right? If I to make it nice, I need to start in the middle and then do some stuff, right? So it doesn't make any sense. Now, well, it turns out that if this is the case, then life is very bad. Okay, so the point here is that this thing is only good if the trees are well behaved, right, or what you call balanced. Okay, so it turns out that as mentioned, if you do it badly, you can be very nasty. Okay, but what you can do obviously is actually to do this thing called balancing. Okay, which means that you write a procedure, take a tree, go in there and balance it. How cool is that? Okay, and every now and then you call it, means you do the operation, you call it. Okay, and that will give you. Okay, so basically, because you are so smart, right? Okay, so you realize that this is a problem. So now the next thing to do is to go and take a binary tree, okay, and go balance it. Okay, now obviously a tree can only fully balance if what? If the total number of elements is exactly, not odd lah. The word is not odd. The odd is what? It's power of 2 minus 1, right? Or something like that. Okay, if you have exactly 2 to the n minus 1, you have exactly the right number of nodes. Okay, if not, basically you can't actually have a perfectly balanced tree. Okay, but then the point now is that this balanced tree procedure must also take care of the situation where the tree is not completely balanced because there's not enough elements, and do some kind of a guesstimated balance. Okay, but even if you do some kind of approximated guesstimated balance, right, you can still achieve basically log n minus 1 plus minus 1 kind of thing. Okay, so you still be roughly log. Okay. Okay. Are we on the same page? Okay. So now that everyone is tired, I'm also tired. I will now take a short break. Okay, and show you a little bit. Yes, we have. Okay, let's take a look. All right.
I'm here to get validated.
You are awesome.
Excuse me?
You have an amazing face. You've got powerful features, man. Anyone ever tell you that?
No.
And listen, you look a little down. And it may seem like sometimes people don't understand you. But someday, man, someday, people are going to see you for what you really are.
You really think so?
Absolutely. You are great.
Need a validation, please?
You are great, ma'am. You have amazing cheekbones.
Really?
Sir, yes. We have a situation. Where?
Oh my God.
What the hell's going on? You've been through it. You know. You've had so much life experience that other people don't appreciate, but you know.
Bless you, dear.
They're not patronizing the shop. They're just coming to see him.
Oh, sir. You're in great shape. You work out?
Not for long.
I do, actually. A bit. Yeah. Thanks.
Young man, we are running a business here, not a social club.
That is a fantastic suit. It really flatters you.
You think so?
You guys work so hard. You are the backbone that keeps this place running.
It always felt like no one really appreciated it.
Yeah, I mean, our jobs are so stressful, and it seems like most of the time people just don't see it.
No, what you do is so important.
You know, I bet the boss would love to meet you.
You are great. You provide hundreds of jobs, sustaining hundreds of families. That's huge.
That's so good to hear. Most times I feel like people don't recognize that. I'm just the big bad man on the hill.
Not at all. You give.
You know, I know some people who would probably like to meet you.
Mr. President, no matter what people say about you, you have still got a great golf swing. God bless you. You do. You have a fantastic mustache. I bet Burt Reynolds and Tom Selleck look at you and get envious. I'm not kidding.
Thank you.
You're welcome.
Hugh Newman, a man who is changing the world with free parking and free compliments.
New leaf. A very big new leaf.
Your license is expired, sir.
That is why you're great at what you do. You are so thorough.
Really? You think so?
Hugh, what is your secret?
I just love to see people smile.
It seems there is no one Hugh Newman cannot make smile. Next!
Welcome to the Department of Motor Vehicles.
Now serving B331 at window number 19.
No one smiles in their driver's license photo, sir. It's not allowed. Next! Next!
You are amazing. You are so efficient.
Next!
Victoria. Oh, that's a beautiful name.
Next!
You take such good care of your equipment. Oh, they're lucky to have you.
We're closed, sir.
Victoria. I just want to see you smile.
Good night, sir.
Where do I go for...
We don't validate, sir.
They match your eyes. Sorta. Oh, you have the most beautiful eyes I've ever seen.
Next.
You eat healthy, too. See, you take good care of yourself. That's awesome.
See, you're even a great pet owner. You're giving her a full hour's walk. Most people wouldn't take the time, but you care. Oh, boy, do you care.
Have you ever smiled?
Yes,
When?
when I was a little girl.
Oh, I bet you had a beautiful smile. What happened to it?
Next!
Look like anyone you know?
Next!
There's color and black and white.
Next! Next!
I just wanted to see you smile.
I'm sorry. Next!
I'm here to get validated, please.
You're... okay, I guess.
Okay. Did you say okay?
Yeah, you're fine.
Don't you have anything else to say?
What's the point?
take our picture? Thanks, I really appreciate it.
It's our first time here.
Smile. It's not a real smile. You guys love each other? You're on vacation, traveling the world? Yeah, that's great. Wish I could travel the world with the woman I love. Wish I could have someone take our picture. I'd really smile. You guys have every reason to smile. You're gorgeous. You're in the prime of your lives. And you guys are great. Hold it right there. Now that is a smile. Hey, one more right there. Oh, that's excellent. One more. Beautiful, beautiful. Here, look at each other. Oh, fantastic couple. What do you love most about your wife?
She accepts me. Despite knowing.
Where did you meet?
On jury duty.
Oh, served your country and met the love of your lives. You guys are awesome. Beautiful, beautiful. Nice meeting you.
So much.
Okay, bye.
Excuse me. You get the most sincere smiles out of people I've ever seen. Do you want to make some extra money shooting stuff like this?
Pardon me, folks. Sorry to interrupt. You're a beautiful couple. Are you model?
No.
Would you like to be? You have two of the most beautiful eyes I've ever seen. Your eyes, they're gorgeous. You're gorgeous. And your dress matches your eyes. Perfect. May I? What do you love most in all the world?
My daughter. She has the most wonderful smile.
Hello. 310 Cleaning. Hugh Newman?
Hello, Hugh. Can you just put your driver's license on there when you're done?
Sure.
Thank you.
Hey, ma'am. How did you... You're smiling. But she... Did you... Excuse me, sir. Where's Victoria?
She doesn't work here. She was fired.
Fired? Why?
You were smiling. Look at this. She did these. Look at that. They're all smiling. Look at that. Those pictures suck. They're not supposed to smile. See? They're all smiling. Look at that.
Where is she? Really?
You are awesome. You're going to have so much fun on this trip. The stories you're going to tell people when you get back will be amazing.
I can't wait. I've always wanted to see Paris.
I don't understand. I tried everything. What happened?
When I was a little girl, my mother got very sick, and she stayed that way. And over the years, she just got so sad that she forgot how to smile. And seeing her like that, I couldn't smile either. And I didn't for years. But then one day, a young man came up to her and told her how beautiful she was. So beautiful that he wanted to take her picture. He made her smile. And suddenly, after all those years, she got better. I looked everywhere for you, but I couldn't find you anywhere. I went to every garage in town. I paid every fee they had, but I couldn't find you.
You paid for parking? For me?
Yes. Because you are great. You are amazing.
No one has ever said that about me before.
Okay, that's all. Okay, so I thought it was a really cool clip. Alright, so let's go. Okay, so what we've seen this, today is that so for one particular object, right, it's possible to have many different representations, sets. Okay, you have three different ways of doing this. And obviously there are more ways than this, alright, but the fact is that you can have many different representations for the same object, okay? So the key thing to understand is this, that each representation has different pros and cons, right? So typically, the general idea is this. The general idea here is that different representations will basically give you different operations, and each operation has its own pros and cons, right? So the question will be, right, somebody asks you, what is the most, sort of the best representation? And what's the answer to that question? The right answer is depends, right? Depends on what? Yeah, correct. So the whole point of this lecture, if you just stay with me for another half an hour, is that the thing that determines which representation is most efficient, depends on the usage. Right, we'll cover this again in recitation, but just keep in mind that there's no best representation. It just depends on what you use the thing for. Okay, so in typical large projects, right, you can actually have, you often have multiple representations, and the reason is for what? Why is this? Efficiency. Different people, right? So there are many possible reasons. Okay, sometimes over the period of lifetime of a project, right, you can have different requirements, and depending on the requirements, you need to change the representation because of efficiency reasons. Because there's no single representation that's good for everything. Okay, and then also another thing is this: the people, no problem. People like to do their own thing, right? Programmers like to rewrite their own thing. So it's not unlikely that after a while, right, you have basically the same things rewritten in several ways by different people. Okay, so this is kind of a fact of life. Okay, so what we talk about today is this: suppose you have two things. First thing is I've shown you that you can have one object and different representations. Now the next part of the lecture we will talk about this other issue. suppose you do have different representations living in some zoo. Obviously, your program has different different types, different variants of the same thing. How do you deal with that? Okay, so you want to ask this question: how do you manage different coexisting? Obviously, one thing you can do is this: as boss, you can kill off 5 of them and leave the one standing, right? But not always practical. So suppose you want to have all different representations. How do you do this? Okay, first of all, what are the issues? Okay, why is it a problem to have these different representations? Okay, and next question is 2 things. First, understand what are the issues. Second thing is understand what are techniques to use that you can use to manage this. Okay, obviously, as always, there are different techniques, and again, there is no best technique. Okay, so the thing you need to do is to understand how the different ways of doing this will have different effects. Okay. Now, so to illustrate this example, we'll use another example, which is the math thing. So last time we saw rational numbers. Today we will do complex numbers. Okay. So who here knows? Okay, wrong. Who here doesn't know complex numbers? A plus bi. Who doesn't know this? Who knows this? Oh, know this, right? Very good. This picture. All right. So basically, complex numbers are the form a plus bi, okay? And typically, you can represent the thing using a Cartesian plane, right? Where the x-axis is the real part, the y-axis is the imaginary part. Okay, so ax plus dy or x plus yi is actually known as the rectangular form. Okay, there's another form which is known as the polar form, right? Which is of the form r e to the I theta. Okay? So r will be the magnitude. Okay, and theta is the angle of this line. Okay. Okay, so this is not new. This one I think I've shown before. The last time we saw this rational numbers thing in terms of layers, right? That was used to illustrate this idea called like abstraction barrier. Okay, now the world looks a bit different. Okay, now it turns out that this is a new world. So it turns out that what happens is the following: you have programs that want to use complex numbers. Okay, and as before, you have four basic operations: your add, subtract, multiply, and divide. Okay. Now, then in order to support these operations, you have this complex arithmetic package. Okay. Now the challenge here is this. The challenge here is that complex numbers essentially have 2 natural representations: either your rectangular form or your polar form. Okay, and what we want to do is now have a system whereby these 2 guys are actually coexisting. Okay, and obviously these 2 guys are sitting here. Why? Because the whole point here is that you are doing addition, multiplication, and division, and you really don't have to care. Okay, when you're writing programs up here, you don't want to care whether or not the object is in which form. You want it to just work. Okay, so this is the general idea. So you want to, and your job now is to basically build this layer. Okay, so the idea is that, so Ben, this imaginary guy in SICP, okay, Ben has built this thing, Alyssa P. Hacker has built this thing, and your job now is to build a layer in between them so that somebody else can actually somehow do these operations without worrying about the different representations. Okay, so this is similar to the previous rational package. Okay, so first of all, let's quickly go through revision of your complex arithmetic. How you do addition? Basically, the addition is very simple, right? To add 2 numbers, you basically add the real part, you add the imaginary part, you're done. Okay? Simple. Now, so addition, obviously multiplication, same thing. Now, next thing, multiplication. What do you do? Well, basically multiplication, you do the following, right? You basically multiply the magnitude, and you do what? And you add the angle, right? Okay, so this is how you do it. Okay, and this is quite easy to implement. Assume that you have the following. Okay, wishful thinking. You have the following thing: you have real part, imaginary part, magnitude, angle, and then you can actually use a constructor that can create these numbers. Okay. Now, so let's take a look at Ben's code. This is the so-called rectangular code. All right. So suppose I want to make an imaginary number x and y. Okay. What I will do, obviously, because it is a rectangular form, is to do a cons xy. Right? because I need to keep track of two numbers, right, x and y. Okay, and then the real part is just the car. Imaginary part is the scooter, right? Now magnitude and angle, how do you do this? Essentially, you just draw the line, right? Magnitude will be the a squared plus b squared, square root, right? Okay. The angle will be what? Arctangent. Okay, because the angle will be y-x, and then you draw the arctangent, right, of the angle. Okay. Finally, you can do what? Given r and a, that means given the magnitude and angle, you can construct this object, right, by doing what? R cosine a and r sine a. Okay, so this is all very simple. Anybody has any questions? I'm not doing anything special here. I'm merely writing out definition of complex number in code. Okay. Okay? Okay, very good. Now let's look at the polar form. Polar form means what? Okay, if rectangular form, I store the number as x and y, where x and y are the x and y components. Polar form, I also store the components, but I store them as r and a. Except that r and a are not the x and y. R and a are the magnitude and the angle, right? So now for real part, if the object is stored in R and a instead of x y, then the real part is no longer what x, right? No longer car, right? Is what? It will be the magnitude times the cosine, and the imaginary part is the magnitude times the sine, right? Okay. On the other hand, because it's stored like this, the magnitude and the the magnitude and the angle, you just do the car and equator, right? Because the storage is r and a, so r will be the magnitude, you carry out, a will be the angle. Okay. Similarly, you can also make this object from a real imaginary by doing what? By computing the magnitude and the angle and then connect it together. Okay, are we clear? Alright, so this is again a translation of the definitions into code. Alright, so there are two possibilities. One possibility is you store it as xy. The other possibility is you store it as r theta. Okay. Now, so suppose there's this world whereby these definitions coexist. So the question now is what are issues? So first thing is the problem of name, right? First thing is the problem of name. Basically, you have a piece of thing, right? You have your operation, it's the same name, then what's happening? See, the problem here is this. Suppose you do it, okay, this thing is called real part z, right? This thing is called real part z. It turns out that this operation, they are different. Okay? So the question now is, how do you actually make sure you have the right procedure? Number two is this, right? Number two is that given an object, okay, both cases is a pair, right? It's a const pair. One is xy, one is RA. You have no idea given this thing, because RA are rails, x and y are rails, right? You get this object, you have no clue whether it's rectangular form or polar form. Okay? So what else is the problem? Okay? These are the two. Then the next thing is, because you don't know which is, okay, the basic problem is this. Given an object, you need to match the operation to the object. Right? So how do you do that? Okay? And the other thing is the name problem, name conflicts, right? So the two key problems. First challenge is this: you have representation, you have the associated operations that operate on the different representations. You need to figure out how to match them. Okay. Secondly, you have naming conflicts. Okay. So the first solution is this. The first solution is this called tagging, which is that if you have this kind of representation, the first thing you want to do is to put a tag there so people know what kind of representation it is. Okay. So what we do is that we will have this procedure called attach tag. Okay, it doesn't do much. Attach tag, all it does is that it cons a tag onto something, an object. Okay, and what we can do is that we can, instead of just consing the two together in the original form, you add an extra tag. Okay, and then similarly, Alyssa, you also attach a tag called polar, and you're done. Okay, so it's very easy, right? So in order to check to check given an object what type it is, you can just do a EQ type tag z, and you can check. Type tag is just, okay, so you look at this. Attach tag does the following. Attach tag takes some object, some kind of data, it attaches a tag to it, okay, by just consing it on top. type tag of a data, right, basically checks whether it's a datum. If it's a datum, then you just you carve out the tag that you attach to it. Right. Now, contents essentially will be following. The contents will just be to take out the header, right? Because originally you have just const the tag onto the content. So this thing will extract the content. This thing will extract the tag. Very simple. Yeah. Okay. Okay, but you still have a problem. You still have this naming conflict problem. So there are two problems. First is the type, which we have solved using the tag. Second thing is, so the next thing is, how do you, even if you know the type of an object, now you have all these operations, okay, you must basically try to figure out how to solve naming conflicts, number one. Number two, how do you map these operations onto the correct object? Okay. So the first thing, obviously, you can do is that you can impose a naming convention, right? Okay. Essentially, you can name all the procedures by forcing them to end with a tag of the name of the tag, right? So you can basically force them to say that, okay, make real from imaginary rectangular, make real from imaginary polar, whatever, and then this basically forces you to know which. So the question now is, have you solved the problem? Is this sufficient? So basically, if you name the procedure properly, then you know lah. So it means that if you deal with this object, okay, and then you know it's a polar object, so you call the polar form of procedure, you're done. Okay, so is this problem solved? Anybody? It's kind of solved, but it's a bit clunky, okay? So the first thing is ask ourselves this, okay, now, basically you have this problem of having data types and operations. So whose job is it to match the data type to the operation? Programmer. Which programmer? The user, the band, or listener. Okay, so there are different levels. Remember, there is users using all these operations. There is Ben who actually did this thing. User's job, is it? No. Somebody else's job. Project manager. So who is project manager? Okay, so this is a saikang for you. Good for you. Okay, so wait, first of all, okay, what are the pros of having the user take care of this thing? The user will have a pain, right? Easier program. Okay, so it means every time you have a data type, you check what the data type is, then you can figure out which operation to call. It's a pain in the butt, right? Alright. Okay, it's a real pain for the user, right? Okay, how about Ben and Lisa? Can they do it? They can kind of do it, but it's a pain for them, right? Okay, because the thing is this, the thing is to think about how to deal with this problem. The problem is that basically if you want them to take care of this problem, what kind of code changes must they make? Okay. They essentially, because you're writing code, any of these guys can do the job. The problem here is that depending on who does the job, what needs to be done is different. Okay. Now, so the thing is this. Okay, if the user does it, it's not nasty, right? So, okay, but let's think about the first thing, user. Suppose the user does it. Okay. Now, if the user does this job, that means what? That means wait, you see what am I doing? The user, sorry, not user. Suppose the job is done here. Okay, I am implementing for you these operations, right? Now, in order to implement these operations, what must I do? I must actually, suppose I add two guys, S1 and Z1 and Z2. Okay, then essentially what I must do? I must extract out the real parts and imaginary parts, right? Okay, so the easy thing to do is do a let. I do a let and I extract all the parts. And how do I extract the parts? Each of them, I check whether it's real or imaginary. If it's real, I will call the real thing. If it's imaginary, I call the imaginary thing. Okay, and after that, I can just basically use this code to go and give you the right answer. Okay, but the general idea here is, the thing you realize is that there's a lot of checking. Okay, now, so how does Ben's code change? Ben basically has to do this, right? He has to do imaginary and this, and it's quite okay. Okay. Now the problem is this. The problem here is the following, right? Ben's code may be removed. basically somehow along the way you decide to dump this library, okay? Or else, and then you left only Alyssa's code. Now, it turns out that after Ben's code is removed, you may want to add in a new form, maybe, you know, I don't know, Ryan form or something, you do another form, okay? And then it may turn out that Alyssa may decide that he wants to make the her representative more powerful, add a few more operations. Okay, so the thing now is the following, right? The problem here is that when people change code, right, then there's a lot of stuff that must change all over the place, which is kind of nasty. Okay, so what's the point? The point here in this particular lecture is to think about this problem, understand the complexity of this problem. Okay, the problem here is that it's not one person who is writing the code, it's several people. Okay, so the real question is, how do you do this thing so that you minimize changes propagating through the code? Okay, so the principle in life is very simple. I'm making fun of this problem. Okay, SF style, right? You're all well trained, okay. So it's called Tai Chi, right? Then it's something else problem. Okay, so and the way that we will go about doing this, okay, is important. Okay, this is the key concept. Is to create this layer of abstraction. Okay, let me just show you. Okay. Now, this idea is called, in this particular instance, it's called generic operators. Okay, and the general idea is that you can create a layer to shield one layer from the other layer. Okay, basically, the general idea is that somebody can create this layer. Can be Ben, can be Lisa, can be the project leader or the project manager. Okay. Now, so this is originally what you saw, right? This is what you saw earlier. It's a bit nasty. So what we do now, okay, you see from here, okay, I'm like a optician. You see this? You see this? Okay. So what I want to do is I want to add in an extra layer, okay, above the two representations, okay, and below the the complex arithmetic package. Okay. Now, so the point now is this. From here, down here, you will use this thing called real part. Okay, this is known as the generic operator. Okay, now the generic operator will do the following. It will do the checking. Okay, and it will do all the contents are hidden from the user. Okay, essentially it will return you only the real part. Okay, so user's code. So essentially, okay, originally, okay, look at this. This is the user's code, right? Correct. This was the original form of user's code. Now in this new world, right, the user's code looks like this. Okay, that means he just does this real thing. Okay, which is actually back to the original version. Okay, this seems to be like the original version. Okay, whereby there's only one representation, right? Okay, now very simplified. Selectors are this, but now the thing is this selectors, the real part and imaginary part, they are known as your generic operators. Okay, because what they do is this: they basically you call one function, the operator will check on the input type of the data. It will basically call the correct operator to operate on the data. Okay, and then constructor you can choose the best one. It doesn't matter. Okay, but how do you implement this? Okay, so the general idea is this. The high level idea is that you introduce a new layer to hide complexity. Okay, and now we will talk about how to do this. It turns out there are several ways to do this. Okay. First way, this is the simple way. This is really the obvious way. It's what you call dispatch on type. Okay, essentially what you do is this: you go. Okay, this is the one I just showed you earlier. Is the obvious one. You look at You look at the data type. Okay, you see what type, and you call for the operator. Okay, it's called dispatch on type. Okay, this operates essentially you can take on multiple forms or what you call polymorphic data, because the data can be a polar form, can be a rectangular form. Okay, and what happens is the following. Basically, the user will call operation on some kind of data. Polymorphic because you can be either rectangular or polar, don't know. Okay, it goes down to the generic operator. Okay, generic operator will do what? It will actually check the data type by looking at the tag. Okay, it will strip out the tag. Okay, and you pass the data to the correct representation. Okay, then the stuff is being done. Okay, and after that is being returned, right? And on the return pass, essentially what we do is we will put the tag back. Why? Because later on this thing will use again by the user, right? And then when it comes down to the generic layer, I need to know where to sharp it. Okay, so it's a very simple idea. Okay, and this is something that you will probably be doing. It's a bit thing to do now. Okay, so first of all, what's the advantage of providing this generic operation? What means what? Basically, the idea is this, right? You write, okay, you see the same idea. Your user write one time, okay, you write your addition operation, multiplication operation, all this once, and user's code doesn't change anymore, right? It never changes. Okay, if Ryan feels shook, he writes another new form. What happens? You just change this, update the layer by adding more cases, right? And then essentially you're done. Okay, with the user of the code upstairs need not change anymore, right? It's kind of cool, right? Whereas in the old case, right, the user code keeps changing. It's a real problem. Okay, so you are actually keeping that. Yes. 2 and 3. No. First of all, given the object, right, is passed to this layer. This layer, which is generic operator layer, will look at the object type. Depending on the type of object, it will know whether to pass this object to this side or that side to do the operation. Okay, what you do is you strip out the layer, you strip out the tag, pass the object down. Okay, the operation is being called at this layer, and then after that, when it returns, the tag is actually tagged back into the data tag, so that later on the data is used again. You know what type it is. That's what arrows mean. Okay, again, this thing. Okay, today's lecture and tomorrow and Friday's lecture seems a bit fluffy. I mean, a bit abstract. Not fluffy, abstract. But you'll be made concrete in your mission, obviously. Okay, so after doing missions, you will have hopefully good idea what's happening. Okay, so the whole point here of this layer is to insulate changes to the underlying representation from the code that's been written. Okay, so the problem is the following. The thing to think about is this. Suppose Ryan writes a new a new representation. What kind of changes does he make? Basically, you have to what? Add in more case statements into the layer, right? Okay, does it resolve the naming conflict problem? No, it doesn't, right? It means that Ryan must still game properly, right? It must be the operator Ryan, whatever it is. Otherwise, all hell goes it's still a problem. Okay, so this is really nasty. Okay, so problems are, first of all, the general operators must know all the types available, right? Because it has to know what it is. It must look at the object, must check, and then dispatch. And then adding a new type means you need to change all the operators to go and call the right dispatch. Okay, which is really annoying, and it doesn't obviously solve the name conflict problem. Okay, so how? Okay, second method. Okay, the first one is the obvious one. Now we're going to less obvious method. The second one is this thing called data-directed programming. Okay, so the idea is very simple. The idea is actually to create a table and do a table lookup. Right, so let's take a look. So essentially the idea is this: the general operator look at the tag on the data, okay, goes to this table to find the correct operation, takes the operation, and applies it. Okay. So to address the problem of naming conflicts as well. Okay. And then it's easy to extend, just add more entries to the table. So let's take a look. So imagine in this case, what we do is this: we create a table in memory, okay, which contains the following. On the left side is actually a list of all the operations you want. Okay, and on the horizontal axis is the data type. Okay, so suppose for now we have operators called put and get, okay, which allow you to basically manipulate this data on this table. So you can do put op type. Okay, op and type are really what? The axes essentially they are the indices on the table. Okay, item is item, okay, that you want to put in the table. And then you get op type, essentially returns you the item at the entry in the table. Okay, I say again, your table is of this form. This is op, this is type. Op type, like xy, tells you a certain pigeonhole in the table. Alright? So you can either put stuff there, or you can take stuff out. Alright? Now, so let's look at how the code changes. So what I'll do now is this. So the code that Ben wrote is similar as what you had before. But what I do is the following. I now have this thing called install rectangular package. Okay, so all this code, okay, is the same as before. No change the name. I no longer have the dash rectangular anymore. No more. Okay, so the names are just the normal regular names. Okay, and then, okay, so this is all inside this procedure, right? So these are what? These are local procedures. Okay, they cannot be seen outside. Okay. Then what I do is this, I define the following. I define this whole set of commands. What I'm doing here is this, I am taking the procedures I defined earlier. Okay. This procedures, real part, imaginary part, and two, these are all defined here. Okay. I create them, and what I do is that I put them into the table using the put command, right? I put real part rectangular here, imaginary part rectangular here, and so forth. Okay. So essentially what I'm doing here is that I have defined the original procedures, but these procedures, okay, are only defined inside this high level procedure, this outer procedure, which means that they are local procedures. Means outside you cannot see. After I define the procedures, I call the put command, I take these procedures and put it into the table. Remember, these procedures are what? Objects, right? Okay. Now similarly, what I can do is Alyssa does the same thing. Alyssa also creates these procedures for polar. You see the name, notice the name, real part, real part. The names are the same. Okay. What I do now is that I will put the same procedures into the table, but instead of using rectangular, I use polar. Okay. So after I run this code, what happens is this. After I run this code, essentially I will have a table somewhere in memory, and I put all these objects, all these procedures into that table already. Okay. Now what happens is this. Number one, there are no naming conflicts, right? Because all these procedures were named inside another procedure, and they were not global, so you can't see. So the thing is that the programmers can happily use your own names. You can use the same names, and what happens now is that the names are living within their own namespace. Okay. Now the installer essentially defines all the operations, and then you place them into the table according to the type. Okay, and operations. Okay. Now you still need tags to distinguish the data types. Okay, but at least there's no conflicts as far as the procedure names are concerned. Okay. The question now is, how do you then write the generic operators to do this? Okay. So what we do is the following. Okay. Essentially, we have this thing called apply generic. Okay. And okay, it all looks very simple. Real part Z, okay, will be apply generic real part Z. Real part imaginary part Z will be apply generic imaginary part Z, so forth. Okay, so these things like magic, the first 4 lines like magic, you just call the thing in the name and it doesn't work. What happens is apply generic. Okay, so apply generic does this thing. Now, what is the dot thing? There's okay, this is the new thing, right? It's the dot. Okay, it turns out that scheme is kind of cute. You can actually have a procedure take in an arbitrary number of arguments. Okay, so what happens is this. I'm saying the following. I'm saying that apply generic would take in minimally 1 argument. Minimally 1. That means you must call it with at least 1 argument, and the argument would become op. Now, if you call it with a lot of extra arguments, all the extra arguments will go into this part called args as a list. Okay, so args could be empty. Okay, if you call apply generic with only 1 argument, args will be empty list. If you apply generic with many arguments, then all the arguments will go into the args list. Okay. Now, type text. What I do? See, the args means what? The args really apply to really refer to the data type. So in this case, args will map to Z, right? And args is what? Args actually is a list. I say again, it's a list. Okay. So what happens here is this: you map type tag onto args. What happens? You are basically taking a list. You apply this type tag to extract all the types. Okay, and this gives you essentially a list of types. Okay. Now, then what you do, once you know the type of the arguments that you are dealing with, the data types, you do a get op type. Op you know from here, tag type from here. So remember, originally what we did was that we had put all these procedures into the table according to the type and the data object. Sorry, wrong. Originally we had taken all these procedures and put into the table based on the operation and the data type. So what you're doing now is that, depending on the op you want to do, and the type of the data objects, you will now extract the correct procedure from the table. Okay, it is possible that it doesn't exist. Okay, but if it exists, then prop will be non-false, right? So if prop exists, it's not false, then you do what? You apply prop to the map of the contents on the arc. Okay, let's take a look quickly. Arc is a list of the data, right? When you map contents onto the data, what do? You are stripping out all the text, leaving only the content itself. Okay, and you take the content, and then you apply the procedure you found from the table onto the content. Okay, if you do look up here and it's false, cannot find, you freak out and die, right? Okay, so before I continue, let me just quickly say a few things. So apply generic essentially retrieves the appropriate procedure from the table. Okay, applies it. Okay, apply, continue say this here. Apply is a scheme primitive. Okay, essentially when you do apply star on a list, it's equivalent to class the list. Okay, so this style of using a table to dispatch is known as data directed programming. Okay, another thing, this thing, the dot thing, it's called the dotted tail notation, whereby you can actually have a variable number of arguments. Okay, so what we're saying here is f(xy) dot z. What we're saying here is that f can be called with, must be called with at least 2 arguments. Okay, but it can be called with more. Okay, everything else that's in excess of x and y will become z as a list. So if you call f 1, 2, 3, 4, 5, 6, x will be 1, y will be 2, z or z will be a list of 3 to 6. Okay, so this is a scheme primitive. Okay, so the question is this: why would you want to do this over the dispatch on type? Why? Yeah, if Brian comes with his own new data type, what happens? He doesn't care, right? He doesn't. Okay, if Brian comes with a new data type, you don't have to care about the generic operators. No change, right? As long as you install correctly, as long as you have all the whole set of functions, it's okay. You can have new. Your data type can be special. You can actually implement new procedures as well. Okay, and you can do the same thing. Right. Okay, who maintains the table? Actually, the table is global, right? Each guy takes care of his own part of the table, right? Okay. Okay, so okay. So we're covering 2 strategies. First one is dispatch on type. Essentially, it's a very simple case statement. Second one is this thing called data directed programming, which means what? Which means that it's a global table. You do the table lookup. Now the third type, is this thing called message passing. So the previous strategies basically view the procedures as intelligent. That means they dispatch according to the type of the data. Message passing is a very different idea. Okay, and it's important enough to think about this. It's the idea that the data is intelligent. That means they know how to act on themselves. Okay, you just tell the data what to do. Okay, so let's take a look at one simple example. Okay, we'll do this in class later, but a simple example is this. Okay, suppose you want to do the following. You want to create an object called xy, okay, which represents your imaginary number. And then now what you do here is that you wrap, instead of original version, you wrap the thing you represent as the cons, right? Cons xy. Now instead of doing that, okay, you create a procedure called dispatch. Okay. Now look at this. What I've done is this: I created a procedure called dispatch. Okay, it does some things, and then in the end I return dispatch. So what is the data type? In the earlier examples, the data was a const structure, right? In this new example, the data is lambda. It's kind of weird, but it is lambda. Okay. Now what happens here is this. Now it is a lambda, and the lambda takes in an op, right? And you see, depending on what op it is, okay. So if the op is real part, you give you x. If the op is imaginary part, you give y. If it's in magnitude or angle, it will give you the right thing. Okay. So the data is actually the procedure, right? And then the thing is that basically the data will accept operations and will do the right thing. Okay? So how do you use this code? Essentially you do the following. You will do, okay, if to do real part Z, you just call Z and you pass it the op type. Okay. So this idea is very important. This idea called message passing is actually the basis of this thing which you will obviously have to learn to love and to do, called object-oriented programming. Okay. So the idea here is that the data are objects. Okay. And the procedures that operate on the data are actually contained within the objects themselves. Okay. So objects talk to each other by passing messages. Right. So this is the general idea. Okay. Now, obviously, this is not the end, right? Okay. But it turns out I'm out of time. So we will be covering an example of how to implement this message passing object in class. Okay. I think it will happen after your midterm. I don't think it will be today. Today I think we talk about something simple. Okay. So can I read this? Okay. Now, so just quickly summarize. So the first two key concepts. First concept is the following: is that you are supposed to appreciate the idea that for a given data type, you can have different multiple representations of the data, and the general idea is that no form is typically better or worse. Okay, the basic difference would be that depending on what data type, depending on what representation you choose for data, the operations you need to define to operate on the data will be different, right? And different operations will give you slightly different time and space trade-offs. Okay. Then the second key idea is this. Second key idea is, suppose you have a large project, okay, and you have different representations floating around. How do you actually manage this problem? Okay. And to understand that there are three key, three key things. Number one is, how do you match the data type to the correct operation? Number two, how do you actually manage or prevent naming conflicts? And the third thing is actually the problem of change. Basically, you need to write code and appreciate. Okay, the problem now is this. In this class, you write once, you forget, right? Fine, forget. Because the exam over, whatever, you just do. Okay, the problem now is in real life, your code typically lives on. Unless the company closes down, then no more. But if your company lasts a long time, the code will live on. And sadly, hopefully you won't be the one who has to clean up after somebody else. But it's a good chance when you go to work, right, you have code that you need to deal with and it's from somebody else, and you will consider spelling for sure. Okay? So the question now is to think about how code changes will affect future implications. Okay, there are three strategies, I'll say again. First is fetch and type, which is a very simple idea. You have essentially an if-else kind of a case statement. You check the data type, you call the correct operator. Second one is that you have a table, okay, where depending on, you look at the data type, you look at the operation you want to do, you go look at the table, take the procedure, apply. Okay. The third one is this thing called message passing. Okay. But what you do is that you look at the procedures required to operate on data are where? Are contained inside the data itself. Very strange, but it's a very interesting concept. Okay. And we'll cover this in representation. Okay. Pros and cons, you must understand. Okay. At the end of the day, understand what are pros and cons. Okay. Now you are not. Okay. This class I will not going to ask you in exam confirm, because okay, I hate to focus on exams, but I must make sure that you understand what I care about. I really don't care about this kinds of things, as in, you won't have an exam question whereby, what are the pros and cons of this such and such. Wow, this. Okay, so these things I really don't care from a perspective of exams, because it's not smart, right? Exams are testing whether your brain got wired correctly or not. Okay, this one tests buffer space. How much buffer space you have in your head, which I really don't care about. Because today, storage is cheap, right? You can, for all things else, you have Google, right? So you can always Google stuff that you can't remember, so it's okay. But what I need you all to develop is really intuitions of a programmer, of a software engineer. Okay, understand that these things have certain implications, okay, to your life. Okay, and how to resolve naming conflicts, and what happens. This is the most important now. What happens when you need to add new operations? Okay. So we're done. Any final questions? Okay, last thing. This lecture, very abstract. Okay? But there's a solution. I mean, I've done this is the sixth time doing it. There's a certain amount of professional. I'm quite professional. So it's very abstract. Half of you are blur, maybe 3/4 are blur. But let me tell you, the fix is on the way. It's called mission 13 to 12, is it? 12 to 15, I think. Okay? So, all the best. Thanks a lot. I'll see you on Friday. Or later afternoon.